Okay, so we just finished our first topic about SIMPLIS as a time domain simulator all the time for every analysis. Next, we're going to talk about the fact that SIMPLIS is a piecewise linear simulation engine and uses piecewise linear modeling. So now we're going to look at piecewise linear modeling. So some of the key concepts: every model used in SIMPLIS is a piecewise linear model. Every nonlinear characteristic, no matter what it is modeled with, piecewise linear techniques using piecewise linear resistors, inductors, or capacitors. Even complex devices such as MOSFETs are just modeled with, a combination of these things and plus a few others. And for example, in SIMPLIS diodes, very often, very usefully, can be modeled just as piecewise linear resistors. So let's get started here. So let's now go to schematic 1.1 underscore AE. So let's go 1.1 underscore AE. So I need, there's also a 1.1 without the underscore AE. This one is what you would use if you have the full version, but in the elements version, you want to click 1.1 AE. So let's double click that. And we'll open up our schematic. So let's simulate that. And again, to launch a simulation, you do simulator, run schematic, or press the F9 key, or hit the run button. Okay. And we're going to look at the load step tab. Okay, so if you go down to the load step tab, look at that. You can see here, let's just look at our schematic and get oriented. So here's our input source. This is a self-oscillating flyback converter. You're going to see this more than a couple times today and tomorrow. And so here's the input source. Here's the energy storage transformer, with the kind of a discrete lumped model. So you can see we have the ideal DC transformer, a nonlinear magnetizing inductance reflected to the primary, winding resistance in each of the windings, and a primary leakage, so reflecting the leakage inductance to the primary winding. You have the main switch, a little snubber, the main output of the flyback. Here's a rectifier. The output, we have a CLC, and then the load is a parallel combination of resistor and current source. And it's this current source that's stepping. So we have a bias, and then we have a current source that steps from 0 up to 1 amp. Okay. And then, here's where we can break the loop. Now notice, in our analysis, we did steady state, AC analysis, and transient. So now we're looking at the transient analysis first in the time domain. So we can see that we have a delay of 100 microseconds, and then we do a 1 amp increase in our step load. Here's our feedback. So resistor divider feedback, we're using a TL431 with its compensation as our error amplifier. We're going back across the isolation boundary with a opto-isolator. And you can see this is a self-oscillating circuit. So here's the main power switch. We're using a secondary bias winding that's providing bias for the primary side, but it's also doing a positive feedback. So as the switch starts to turn off, then this positive feedback accentuates that. All right, and it's self-oscillating, so that means the switching frequency is a function of input voltage and output load. All right, so now what we want to do, so we're talking about piecewise linear modeling now. So here we're looking at the magnetizing inductor current in the time domain, and we can see here the load step. And let's just take a look. So I'm going to look here. So we start out in steady state, and again, it's a really good steady state. we go and we take a step load, but look what goes on with the current. And this might be a more, to kind of help us get oriented. So here we're looking at the drain to source voltage of the main switch. Here's the drain current. So during the on time of the switch, we're storing energy in the magnetics. During the off time, that energy then gets delivered to the secondary. And we'll take a look at the secondary current here in a minute. So everything's cool when we start out, but then we go to that load step and notice what happens. We get this big spike in the drain current. And that's because now our transformer is going into saturation. So if we look at the current in the magnetizing inductor, it is this red curve here. Now, again, if we look at the flux linkage of that device versus the magnetizing current, now we see what's a hard saturation characteristic rather than soft saturation like we saw in the sync buck circuit. Okay, so here we're in the linear range, and then we get into the knee of saturation, and then we're into hard saturation. So you can see there's 3 piecewise linear segments that are used in this case to model the nonlinear characteristics of the magnetics. SIMPLIS does amazingly good job on nonlinear magnetics. It's just wonderful. Again, the slope in the flux linkage versus current plane is the inductance. And again, flux linkage is the same as volt seconds. In this case, it's volt milliseconds. Okay. So if, and you can in this, so the slope here, so if we take 1.1 milliwebers divide by 0.4 amps, that is a 4 millihenry slope. Here, if you do the math, you'll see that it's a 1 millihenry slope, and here you'll see that it's a 100 microhenry slope. Okay. So let's look at this in a little bit more detail. So we're going to look at a combination of this curve and this curve, all right? So we're going to zoom in around here, okay? So we're going to look at just one cycle. So when we turn on, the current in the magnetic is equal to 0. And so this is in the time domain now. So we start a linear ramp. When we get to the 400 milliamps, which is 400 milliamps, then we start to go into the knee of saturation, okay? And we see this slope. So if we say point B is when we get to 400 milli, then that's here. Now you can see the slope changes. And then in the time domain, once we get to point C, which is 450 milliamps, we go into hard saturation. And so now you see the slope really start to peak up. And then at point D is when we turn off and start to come back down. So now the current in the magnetizing inductance is going down. We hit point C again. And now we get into the knee of saturation. At point B, we're back into the linear range here. So you can see this is how we model nonlinear magnetics. It's always done in the flux linkage versus magnetizing current, which is really cool because I typically know what inductance I want. So that's often here. And then as I start to pick a material, then you can start to describe what's gonna happen when you go into saturation. Very, very powerful way of modeling magnetics. Okay, you'll notice that it doesn't include hysteresis loss. So this, I said this is proportional to the BH loop, which it is, but it doesn't have the width of the BH loop. To model the losses well is what we work on doing in our magnetics design module, which we have some really good webinars on that, but we just won't have time to go into in this course. All right, so that's magnetics, but you can see the piecewise linear characteristics. Let's look at MOSFETs and diodes, and we'll start with diodes. So here, so this is the forward voltage of the rectifying diode, okay? So here's my rectifying diode. Here I have a floating voltage probe, a differential voltage probe. So even though this is bouncing around relative to ground, I can easily measure just the forward voltage across the diode. And here's where we're measuring the forward current, okay? So when the diode is off and no current's flowing, the voltage is a little less than minus 22. Then when this switch turns off, and now the energy that's stored in the magnetic is first used to charge the parasitic capacitances, and then it turns forward biases the diode, and now you have current start to flow in the secondary rectifier in the second, and this is the main. So this is the main winding. There's also current flowing in this other secondary winding at the same time. And the astute observer will notice there's a little kink in the current characteristic. And right where that kink is where the current in this other secondary winding goes to zero. Okay, which is very realistic. You know, that if you have sat with flybacks for any length of time, you will have noticed that phenomenon. But we're going to focus now on how do we model that diode, that rectifying diode. And the way we do it, so we model it in the current versus voltage plane. And so in red is what you see is the SPICE model, you know, and in blue is the piecewise linear approximation to that characteristic. And so SIMPLIS never sees the red curve. In SPICE is actually solving the red curve. It's solving this exponential. SIMPLIS never sees the red curve. It only sees the blue curve, okay? So it's always solving a set of linear, you know, system. It's solving a linear system at all times. That linear system can radically change, you know, like the slope of this curve can radically change at any moment. But at any point in time, SIMPLIS is solving a linear system, which is why it can get such a high degree of accuracy. Okay. So you can see this approximation is quite good, you know, when we're conducting, I don't know, more than say 1.5 amps or so. It's good in the off region, but it's you know, you could argue it's a little shaky in the knee region. The question that is really important to emphasize is that when you're modeling parts in SIMPLIS, you're always looking for the lowest level of complexity that will still achieve the required level of accuracy for the simulation objective at hand. All right. So you always want to be asking, why am I running? You know, I just pressed run, but what was I looking for? Why am I doing that? And then is there anything I can do to kind of optimize the modeling of my power components to achieve that? And so the question that I have for everybody is, how much error does this introduce? Does this, because you could argue that, you know, that's could be serious error. How much is that going to affect my results? Let's say I'm concerned about either my Bode plot or the step load change. And the way you need to think about this is, well, how much time do I actually spend in this portion, this operating region of this model in my simulation? And when you think about it, when do I go through this knee? Well, I go from turn off to turn on. So we're off and now we're turning on. How much time do we spend going from 0.7 volts to 1 volt, say? And the answer is not much. Not much. It's the amount of time, this slope to go from here to here. That's how much time my model is potentially contributing noticeable error. It's very small. And so what the answer in this particular case is, under these operating conditions, is you could always add more piecewise linear segments. There's nothing magic about 3. What we found is, for diodes, 3 turns out to be an answer that's almost always just what you need. And it doesn't add too much complexity, but it gets you good results. And so when we do our automatic model extraction, we use a 3-segment piecewise linear resistor to model the diode. Similarly, how much error happens when we're going from 1 amp down to 0? Is that error going to be significant? And in this case, the answer is no. You would not. You could add another 1 or 2 piecewise linear segments to this characteristic and rerun the simulations. And if you looked at the Bode plot and you looked at your step load change, you would not be able to detect the difference. So in that, and you can always run those experiments. But then once you figure out, okay, 3 piecewise linear segments is what I need, then don't just do 5, because the more piecewise linear segments you have, as it will slow down the simulation. In real simple stuff like this, you won't notice it. In more complex things, you will. So, key items. And Matt, you're going to interrupt me if we have any questions that need to be addressed, right?
Yep.
Okay. So, conclusions, key points. Every device that's used in a SIMPLIS simulation behind the scenes has a piecewise linear model, right? And so that's just really important to know. It's always piecewise linear, okay? And resistors, capacitors, inductors are the fundamental building blocks for most of that. We have a few other items that we'll look at here in a minute. And even things, as we'll see, like MOSFETs, can be represented with, in a piecewise linear fashion and get quite nice results. Okay. So,
Tom,
yes,
we actually just
yes.
had one come in, I think is a good spot for it. Somebody was
Perfect.
asking about how can we comment on how SIMPLIS models the reverse recovery of diodes?
Okay, ask that one more time.
Can you also comment on how SIMPLIS models the reverse recovery of a diode?
Yes, we can. And we will come back to that again. Yes, we're gonna talk about that in some detail when we do look at the accuracy of piecewise linear models. But what I will say is, the model that we just showed, this model that we just showed, does not include reverse recovery. Okay. You can use a more complex model that we have that does do a really nice job of modeling reverse recovery. And Matt, I believe, Matt, maybe you can say as to when, has added a new feature to SIMPLIS that is going to be available in when, Matt?
So we've created a reverse recovery model that can be utilized in version 9.2 when it is released.
Right. So in our next release, we're on 9.1 now. In our next release, which we're working feverishly to bring out as quickly as we can, Matt's put together a really nice tool so that if you have enough information, and that's a big if, a lot of data sheets just don't have enough information. And even SPICE models often don't have enough information. But if you do have enough information to create a good reverse recovery model, then this new tool that Matt's created will do a very nice job of modeling reverse recovery. And I'll show you an example of that here, in our next, not the next topic, but the topic right after that today. So that, very good question. Thank you.
I would point out one thing also when you showed the modeling of diodes. I once had a customer send me a schematic that was peppered with two N2222s used as an amplifier. They were wondering why the amplifier looked more like a switch than an actual amplifier. So you might want to point out that too, where if you're going to model a transistor, you might need a ton of segments to be able to get it to work quite right.
Right. So our model extraction is focused on modeling the critical portions of the power stage of a power supply. So we optimize our modeling of MOSFETs, for example, and diodes, in this function here, where they're, rectifiers or switches, controlled switches. We don't optimize our, the extraction for use in linear circuits, for example. So it does, we're not going to talk in the course about modeling bipolar junction transistors like a 2N2222. We do have, and I can show you this. All right. This is a 2N2222. And if I double click on that, you have to model that using a model level 2. It's possible to model it as a model level 1, which will model it just as a switch. But in this case, you need to model it with the active region. And so you have to model it as a model level 2. Otherwise, this circuit doesn't work well. All right. So if you want to model a IC op amp and you've got 25 transistors in there, SPICE is a better tool. SIMPLIS is not the tool to do a transistor level model of a op amp, for example, because we're optimized to do switching power supplies, literally SPICE was created to model op amps. All the early applications were all op amps. So it's still the best at that. Okay, so we've seen piecewise linear modeling. Now we're going to do multi-level modeling. Okay, so go to topic 1.0.3, multi-level modeling.